We are now going to look at the calculation of free energy under non-standard state conditions, or free energy non-standard state. And let's go ahead and kind of remind ourselves what we mean by well, let's look at the equation in which the delta G free energy equals, this is a free energy under any concentration, equals the free energy standard state value, which there is only one unique value to the delta G naught, standard state free energy, in which everything's under standard state as far as the reactants or products go, equals R, which is our thermodynamic R constant. And that R constant, let's just go ahead and write that down. That is the value that's in joules at 8.314 joules per mole Kelvin. That's a thermodynamic R constant. Temperature must be in Kelvin in order to match units with our R constant. The natural log of Q, and Q is our reaction quotient. And this is a general equation for calculating free energy, in which the free energy under any condition equals the standard state free energy RT ln Q, the reaction quotient. Now, what defines something under standard state, the delta G naught, is when we know by definition if the reactant or product is aqueous, it's at 1 molar under 1 atmosphere pressure at defined temperature. If the reactant is a gas, it itself is pure at 1 atmosphere under a defined temperature. If it's solid or liquid, those states of reactants and products do not appear in the equilibrium or in the expression, but they would be pure under 1 atmosphere. So that would be the standard state free energy, and the free energy associated to non-standard state is if any of those reactants or products are not at standard state. So let's go ahead and look at the problem that we're going to be calculating. What is a non-standard state free energy of a process shown below here, which is ammonia decomposing or going to hydrogen and nitrogen. We are given the delta G naught, the standard state free energy, 33 kilojoules per mole, the temperature, and then if we look at the partial pressures of hydrogen and nitrogen and ammonia, we identify that we're not at standard state conditions, because at standard state conditions, all these partial pressures would have to equal, by definition, 1 atmosphere. But they're not all equaling 1 atmosphere. Even if one of them doesn't equal 1 atmosphere, we're not under standard state conditions. And then we have to go to the generalized equation. So let's go ahead and determine this. So let's, we're going to go ahead, let's write our reaction down, in which we have ammonia and in equilibrium, or in with H2 gas, and not equilibrium, but in an equilibrium process, not at chemical equilibrium, equals delta G plus delta G0 plus RT ln Q, okay, which is our action quotient. So the reaction is reversible. We're not at chemical equilibrium, and we're asked to identify what that free energy is. So we're going to go ahead and identify Q, the reaction quotient, and the reaction quotient equals H2 cubed multiplied by N2 based on the law of mass action divided by ammonia squared. Q, our reaction quotient, equals, based on our values, the hydrogen was 0.25, and that is cubed, multiplied by the nitrogen, pressure at 0.870. I am dropping the units because the reaction quotient, as well as equilibrium constants, are unitless, divided by the ammonia, which is 12.9 squared. So our reaction quotient here equals 8.169 times 10 to the minus 5. So we have our reaction quotient, and we're going to go ahead and make sure we have all the other parameters. Our temperature, it must be in Kelvin. So let's go ahead and make sure that our temperature, we were given our temperature at 25 degrees Celsius, and let's add 273 to it, and that equals 298 K. That's the temperature. Our constant we have, and we were given our standard state free energy. So all we need to do now is plug in our values, in which delta G equals. Now we do want to track our units. Our standard state free energy was given to us in kilojoules. So if we go back, we want to make, and we do need to match units. So this value here, we need to be careful about that. It's in kilojoules, and our R constant is in joules. So one of the others we have to convert into the same orders of not same orders of magnitude, but into the same relative units. So I'm just going to go ahead and let's put our delta G naught into joules. So that would be taking the 33.0 times 10 to the third to the 3, and that would be joules per mole, plus R constant, and that's what's defining the other units here, at 8.314 joules mole Kelvin. T is at 298 Kelvin, and the natural log of our reaction quotient at 8.169 times 10 to the minus 5. Okay. And therefore the delta G equals, so let's go ahead and kind of make sure we're tracking our units here. The natural log is unitless, K's leaving, the Kelvin's gone, and we are in joules per mole. And so our free energy, the delta G non-standard state, equals a 9,680 joules per mole. And if we were asked to convert or express the answer in kilojoules, then we'd move that value over 3 decimal places, and the delta G non-standard state equals 9.68 kilojoules per mole. And that is a calculation of a non-standard state free energy, the value of the non-standard state free energy.